So when we're investigating linear programming, we are bound by a feasible region by lines called constraints. So P to R is a constraint, R to V is a constraint, O to V is a constraint, and O to P is a constraint. And we are, right now, please copy this graph onto your notes. And then after you copy it onto your notes, please label the points V, O, T, and R. And please write the X and Y value. For instance, T is a point 0, 1, 2, 3, 4, 5. R is a point 3, 6. And V is a point 1, 2, 3, 4, 5, 6, 0. And O is 0, 0. And I want you guys to write C is equal to 2x plus 4y. So on my notes, this is what I wrote. So my question now is, which of these points, T, R, O, and V, would maximize our objective function here? So what we're going to do is we're just going to start plugging in values. So let's write this. At 0, 5, C is equal to 2, 0 plus 4, 5. What did we do? We took our point T, 0, 5, and we're plugging in our X's and our Y's. So which of these 4 points here, O, T, R, and V, O is the origin, would maximize my objective function? Now again, we had a bunch of values in between. We could have tried S. Remember there's an S here, there's a U here, there's a T here. No, not T. Sorry, do I call that P? Oh, actually, no, I messed up. This is actually T, and this over here was P. I copied it wrong. Okay, sorry about that. I can tell you this, S, V, and T, we're not gonna optimize, we're not gonna maximize my equation. We weren't going to get the highest return. So our next one is going to be at 3, 6. What would be our objective function? At 3 plus 4, 6. And at 6, 0, C equals to 2 times 6 plus 4 times 0. And at 0, 0, C is 2, 0 plus 4, 0. Okay, I want you guys to spend about 2 minutes and tell me which of these would be the maximum C value. And once you have it, go ahead and type it in the chat. Our restraints, again, X is 0, so we're going to the right. Y is 0, so we're going up because we're greater than it. And we're given these 2 line equations here. And turns out, if you solve for y, you can graph these lines, like here, and then graph this line like right there. Okay. So we're gonna end up graphing these lines in Schoology today. Now, if you look at this other example here, they ask for find the minimum and the maximum value. So they ask you to find both. Now, look at the picture first. How many vertices do we have? We have one at 0, 8. We have another one at 0, 0. We have another one at 8, 0. Okay. So the cool thing about linear programming is that you only have to plug in the vertices. You don't have to plug in any values in the middle. You don't have to plug in values on the line. You only have to plug in values on the vertices. And if you look at the solution here, to find the maximum and minimum, they did what we did. They plugged in 0, 0 into our objective function. They plugged in 0, 0, 8, 0, and 0, 8. And we got the values like we did, similar to them. And we have to ask ourselves, answer the prompt. The prompt says find the minimum and find the maximum. Okay. So why is this kind of important? This problem always comes up, the manufacturing bicycle program. So two manufacturing plants make the same kind of bicycle. Right? Two plants make the same kind of bicycle. The table gives the hours of general labor, machine time, and technical labor required to make one bicycle in each plant. For the two plants combined, the manufacturer can afford up to 4,000 hours of general labor, up to 1,500 hours of machine time, and up to 2,300 hours of technical labor per week. Plant A earns a profit of $60 per bicycle. Plant B earns a profit of $50 per bicycle. How many bicycles per week should the manufacturer make in each plant to maximize his profit? Now, this question has a lot to it. Like, why does this guy have two plants? Okay. Now, why does it cost more to make, why is it more profitable to run one bicycle versus another? Right, one's $60, one's $50. And if that's the case, why don't you just keep running bikes off plant A? So when they give us a situation, you'll see here that they end up drawing a graph with a couple of restraints. We have 1 line, 2 lines, and 3 lines. Okay. And the profit would be here, $60 for plant A bicycles, $50 for plant B bicycles. And when you add them up, that's how much we're going to make. That's our p-value. Okay, so the idea here, my objective function is I'm saying, hey, what is my maximizing profit here? So they gave us a couple constraints here, right? And if we graph them out, we end up with a graph up here. And this is what all we do. After we draw the graph, we plug in all our vertices into our objective function. So first point, 0, 500, right here, look, 0, 500. Plug in 0, plug in 500 for A and B. Next point, 300, 400. We plug in 300, 400 for A and B. So instead of checking all the possibilities, we only have to check the vertices. So how did they come up with these constraints here? They're from the table. So let's take a look for our plant A, okay, and B. So here's the idea. The boss can only spend so many hours in general labor. So let's say he has 1,000 people, and he can only set these 1,000 people to either plant A or plant B. So to make a plant A bike, look, it costs 10 general labor hours to make one versus a plant B bike, which only costs 1 labor hour. So we say 10A down here, 10A plus B has to be less than 4,000 hours. So up here he said he had 4,000 hours of general labor that he can use, and he has to share this amongst the 2 bicycle plants. So I'm going to stick a couple in A and a couple in B, but these hours have to be less than 4,000. The second one, machine time. In plant A, machine time only takes 1 labor hour versus 3 for plant B. So how much do we have for machine time? Looking here, up to 1,500 hours of machine time. So number of hours in A versus number of hours in B, so number of bikes made in A versus number of bikes made in B, that has to be under 1,500. And then the last one, technical labor. to make a bike in plant A, that's 5 hours. To make a plant in B, that's 2 hours. But remember, you can only have 2,300 hours total. So if I make one bike in plant A, I've already used 5 hours. If I make two, I've used 10 hours. If I make three, I've used 15 hours. So we have this time, 5 times A plus 2B. These technical hours have to be less than 2,300. So if you look at the possibilities here, the vertices tell me what my possibilities for A and B are. If I make 0 A bicycles and 500 B bicycles, would that be the most profitable? So let's plug it in. If I plug in 0 here and 500 here, we end up with a profit of 25,000. Okay, sounds like a lot. But if I try the other ones, if I split my values, 300 for A and 400 for B, hey, I actually made more money. What if I make 380 for A and 200 for B? Oh, that's not as much, but that was still more than our 25,000. And if I go to 400 and 0, that's going to be 24,000, which was less. So you want to check all your vertices because you don't necessarily always know which one will give you the most. Once you get more familiar with this, yeah, you can actually have some intuition. But till then, we plug them all in to make sure we can find out the maximum. Okay. So for IXL today, your homework is actually pretty simple. It's doing a lot of the work for you for like most of the problems. So let's go ahead and read this prompt. Look at the system of inequalities, and they gave us y is less than negative 4x plus 8. To graph this, our y-intercept is 8. You guys all go with this 8. And the slope is negative 4 over 1. Negative 1, 2, 3, oops, sorry, negative 1, 2, 3, 4 over 1. Yep, negative 1, 2, 3, 4 over 1. They graphed it for us. They said y is less than, so is that shade above or below this line? We are shading above y or below y? Shade below y. They also told us two more constraints. X is greater than 0. X is 0 here. So X is greater than 0 at 1, 2, 3. So we're going to shade to the right. Y is greater than 0. So here's Y is 0. I'm going to shade up here. Now, I'm going to go ahead and show you guys how to graph this real quick. There's probably a, let's get there, jump ahead. Nope, they don't have it in this one. I'll show you another one.
Mr. Ko, for this one, where it doesn't have the graph, do you have to like graph it on a separate piece of paper to see where the vertices are?
Yeah.
Okay.
There's actually a way of solving it. I'll show you guys how to solve it in just a moment. I'm just trying to get to that graphing application to make it easy to look at. Okay, so here is an example of something very similar. They give us constraint 1, 2, and 3, okay? 1, 2, and 3. And they gave us, here is our objective function. This is the one that we want to maximize. So the cool thing about IXL is that graphing these prompts is super easy. Let's graph this line here. What's my y-intercept and what's my slope? My y-intercept is 9, so put a dot 9. The slope is negative 1, down 1 over 1. Solid or dotted, these are all going to be solid lines. Okay, that's done my first line. Let's pick my second line. 6, slope is negative 1, 1, 2, 3, 4. Done, cinch. Last one, 1/2 x. My y-intercept is 0, slope of 1 over 2. Now, IXL makes it easy that you can just, shade parts. But I want to just go ahead and go over this, how I taught shading before. Let's do our first line. Y is greater than this line here, this blue line. So what's greater? Isn't all these parts greater? Okay, followed up with what is less than the second line? So not only do we have to be greater than the first line, but to be less than the second line. Okay, well this part isn't less than, this is not less than my green line. So now we're left with only 2 parts left. Now y has to be greater than my purple line. I'm colorblind, hopefully that's purple. So it can't be this one. So we're left with those constraints. Now the cool thing, if this was asking us to optimize our linear, if this is a linear programming problem, I can say, hey, my vertex is at 4, 5, 6, 3, and 8, 4. So the question now is, what are the x and y values that minimize my function for this feasible region? So what you would do now is write down our points. My vertex is 4, 5, 6, 3, and 8, 4. And you would plug it into this equation here and find out which of these 3 points would give me my lowest answer. Why did I say lowest? Because the question at the end was, what was my minimum value? So can you guys do that right now? Write down the points 4, 5, 6, 3, and 8, 4. And then you're going to minimize that.
Mr. Co?
Yep.
Could one of the shapes with the vertices, could it be like, I think it was like open-ended or something? I don't know what it was
Yeah,
called.
it
But
was
what do you do?
unbounded. Region was
Unbounded that.
unrestrained. Yeah.
So,
So they wouldn't ask you a minimum for that then.
but how would you know like the vertices? Would you just do the vertices that like you know?
Yes, you only check the vertices that we know.
Okay. So like if it's like a triangle, one of those triangles that are unbounded, you just do like the top of the triangle, so then that's
Yes,
already the answer?
just do the vertices that you have. That's it.
Okay.
So I went ahead and wrote down the objective function. And then we're going to check our vertice points. I saw it as 4, 5. And then we said 8, 4, and 6, 3. So we're going to plug it in, minus 4. Oh, that's a y, I'm sorry. So minus 5. F would be 8 times, what am I doing? 9 times 8 minus 4. And 9 times 6 minus 3. Okay, I got an answer from Alex. Okay, so what's our minimum? Our minimum is our 4, 5. Let's practice another graphing problem. We have my y-intercept is 4, and my slope is -2 down 2 over 1. That's my first graph. We have x here is greater than 0. So x is greater than 0 is going this way. It's a vertical line. And y is greater than 0. Oops. Y is greater than 0. Now we have to shade. Now we're less than my blue line, but bigger than my x and y. Okay. Now in this case, we only have
Wait,
3
are you
points
showing
to
us
check.
the IXL?
Yeah, oh, sorry.
It's not. Oh.
Yeah, you're right. I didn't share it. Sorry about that. Oops. Let me just redo this problem. Oops. Let me get to another problem. Let's graph this one, okay? So my y-intercept is 6 for the first one. My slope is -1, down 1 over 1. My x is greater than 0. So when x is greater than 0, that's always a vertical line. My y is greater than 0, that's always a horizontal line at 0. And in shade, we're less than our yellow line, so we're here. So the cool thing about this problem, there's only 3 vertices. There's 3 constraints. Turns out we have 3 vertices. So you only have to plug in 0, 6, 0, 0, and 6, 0. We have to read the question. What is the minimum value of this function? So which of these values do you think would give me my most minimum? And you might say 0, 0. But look at this function here. 4x minus 6y. I want you guys to spend a moment to think about this. 4x minus 6y. If I want the smallest value, who do I want more of? X's or y's? Which of these would give me a smaller value? In a sense, which of these would hurt me more? A +4 or a -6? So if I was plugging values, let's say if I give you x is 1, x is 2, x is 3, right? X is 1, x is 2, x is 3. Is that going to make 4 times those numbers bigger? Yeah, and those will be positive numbers. But the y values, if I put y is 1, y is 2, y is 3, that becomes -6, -12, -18. Those hurt me more, right? Those make my numbers smaller. And so Aaliyah said that -6 is actually right. That -6y, that's gonna make my number even smaller. So the more y's I give it, actually the smallest number will be. So it turns out my answer is actually going to be 0, 6. Because at 0, 6, my x's are 0, so it doesn't give me any plus values. And that y being +6, 6 times -6, gives me a -36, the smallest value possible. So you can actually do these problems without plugging any numbers in, if you can read our optimizing function and see which one's going to benefit or hurt us the most. It's going to be 0, 6. So you write it as a point. 0, let's see if I write it as a point. 6. Oh, they wanted, sorry, they wanted the value. I should write that better. They want the actual value. So when you plugged it in, it would be -36. Okay. Now for this IXL practice, a lot of it is just pretty easy. It's just name the vertices. So not this one. Yeah, this one. Like the first one, it just named the vertices. 0, 0, 0, 2, and 4, 0. Name the vertices. Now this question is, what is the minimum value of the function for the feasible region? Just like what we looked at before. So given these constraints, if I plug in my vertices to this objective function, which of these values do you think would give me my smallest? Okay, without actually plugging anything in, can you guys think about which of these points, 0, 0, 6, 0, and 2, 0, sorry, 0, 6, and 2, 0, would give me my smallest point? Look at the +2x and the -8y. We're trying to find the smallest value possible. So in the chat, if you can tell me which point works, 0, 6, 0, 0, or 2, 0. Let me ask you a different question. If you want to get the smallest value possible, do you want more x's or do you want more y's? If you want the smallest value possible, do you want to put more x's here or you want to put more y's here? I'm seeing y's because the more y's I put, the smaller my number is because it's going to be a greater negative number. Right, Aaliyah? So my point here with the highest y value is actually going to be 6 So 0, 6. When I plug in 0, 6 in the question, they give me negative 48. The same question here, similar. They're going to ask me this time, what is the x and y point to minimize the objective function? Now, if you look here, you want to be careful here, because if I plug in x is negative 8, doesn't a negative 8 and a negative 2 become a positive? So this one isn't as easy to look at. So for this problem, I would actually write down the possibilities. I would plug in negative 8, negative 5, right? This is negative 8, negative 5. I would plug in negative 2, positive 1, and I would plug in negative 2, negative 8, and just test those 3 points and figure out which of these would be the smallest value possible. In this case, I'm thinking maybe it's going to be this guy here. Negative 8 times 2 would be negative 16. That's pretty negative already. But maybe, you know what, negative 5, and nope, that would be positive 16. That's too big. So I'm going to go on a guess. I'm going to guess negative 8. Oh, sorry, negative 2, negative 8. Because the negative 8 and the positive 2y become negative 16. That's pretty negative to me. All right. Okay. So that's what you guys are going to do for IXL. For the second one, let's take a look at the first one. This one is finding the vertices. So the first part's easy because they gave you the graph. Like I mentioned, they gave you the graph before. So that's not the hard part. The hard part is when we get to a point where they don't give us the graph. Okay. So for this problem, they did not give us the graph. So here's how you come up with the points. You combine 2 of these equations at one time. Okay, so go ahead. If x is 0, can you guys all plug in 0 for me? What's y going to be? Y is going to be 0 plus 2 is 2. That's on vertex. What if y was 0? If y was 0, we would be left with negative x. Moving it over, x would be 2. And then how about these 2 equations here? If x is 0, y is 0. Those are 3. This one's a little harder. When x is 10, plug 10 into this equation here. 10 divided by 2 is 5. Negative 5 plus 9 is 4. X is 10. Y is 4. If I plug y in here, that's 7. If I have to subtract 2 to both sides, sorry, subtract 9 to both sides, let me write this down. Then I have to switch screens, forget it. Minus 9 will be negative 2. Multiply negative 2 to both sides will be 4. X is 4. Y is 7. And if I combine the first and the last equation, x is 10, y is 7. We're just combining all the possible equations. Combining the first and the top. If x is 0, right, x is 0, y is 6. Combining y, if y is 0, you have to move the negative 2x over, it becomes a positive 2x. That means x is 3. And combine the last two, 0, 0. Okay. Now the problem is when equations come like this. So we use substitution for this. So we say y is equal to x plus 1 and y is equal to 1/4 x plus 7. And we're just combine those together. So I'm going to write that down real quick. Why don't you guys try writing this down on your notes? And this will be our last problem. Okay, so this is actually pretty easy. So just make sure you remember what we did before. We're gonna solve for these two first. Y equals to y, isn't that true? Y is equal to y. So we're gonna say this y is x plus 1 is equal to this y, 1/4 x plus 7. We combine the x's to both sides. I'm gonna move these x's over. Some of you guys, here's a trick. If you don't like the fractions, you can multiply everyone by that fraction, the common 4. So if I multiply everyone by 4, x plus 1 equals to, sorry, I ran out of space. If I multiply everyone by 4, this fraction goes away. And that's one trick that some people like to do. It makes the problem bigger, but it does remove the fraction. So multiply 4, 4, 4, 4, and then the fraction is no longer a problem for us. Okay, x equals 8. Now here's the cool part. If I know x is 8, we can plug it in to find out what our y value is. If x is 8, 8 plus 1, that means y is 9. Well, we found 1 point. Now we have to find all 3 points. We're going to combine the next two equations. 1/4x plus 7 is equal to 4x minus y, minus 8. Multiply all sides by 4. X plus 28 is equal to 16x minus 32. Move the x's together. It's going to give us minus x, 15x equals to 28 minus 32 plus 32 plus 32. 15x is equal to 60. That means x is 4. If x is 4, we can plug into any of these equations. I'll plug it here. 4 times 4 is 16 minus 8. That means y is 8. So you would do this for all 3 sets. Last set would be these two, first and third. So we set them equal to each other and then solve for x, followed by solving for y. And that's it.